Acidity of carboxylic acids. A carboxylic acid dissociates in water to form H3O plus or H2O and H plus and carboxylate ion ROO minus. So the reaction is reversible. Carboxylic acid is relatively a weak acid because it can release the H plus. However, it is stronger than phenol and alcohol. Carboxylic acid is a weak acid, but the acid is stronger than phenol and alcohol. So this is the order. Carboxylic acid is stronger acid than phenol, stronger than water, stronger than alcohol. The acidity of carboxylic acid is influenced by resonance effect and inductive effect. So if you look at here, carboxylic acid can release the H plus to form carboxylate ion. The carboxylate ion C double bond O minus, or the position of C double bond O can be changed to this oxygen as well. So any O, the O on top or the O at the bottom. So we call these two resonance structure, carboxylate ion, and then H plus H2O is H3O plus. Look at the value of Ka. The value of Ka for carboxylic acid is the lowest. For phenol, dissociates in water, release the H plus, reacts with water, it becomes H3O plus, and this is phenoxide ion. This is phenoxide ion. And the resonance structure of phenoxide ion was shown in the previous chapter, alcohol. In the alcohol chapter, you can look at the negatively charged can be transferred to the carbon in the ring. And for alcohol, alkoxide ion, release H plus, it becomes RO minus. This is what we call alkoxide ion. The H plus release is react with H2O, so it becomes H3O plus. This alkoxide ion, the negatively charged oxygen is the negative charge is only at the oxygen. So the negative charge cannot be transferred anywhere like phenoxide ion and carboxylate ion. We're looking at resonance effect of the carbonyl group because the acidity of carboxylic acid is influenced by resonance effect and inductive effect. So let's look at the resonance effect. Here, the carboxylate ion, this is carboxylate ion, due to resonance stabilization of carboxylate ion means the negative charge can be at this oxygen or this oxygen. Okay, here oxygen on top or oxygen at the bottom here. It can be at any, so we call it resonance stabilization because the electrons are delocalized between these two oxygen atoms. Or you can also draw like this. The negative charge can be here or here, any at these two oxygen atoms. This is what we call resonance stabilization, resonance effect. This is for carboxylate ion. For phenoxide ion, the one that we've learned in alcohol, phenoxide ion has only one oxygen atom, electronegative oxygen atom, only one. The carboxylic acid has two oxygen atoms. A phenoxide ion, only one oxygen atom. So the negatively charged, you can put this here and on the oxygen and delocalize within the benzene ring, carbon within the benzene ring. But for water and alkoxide, it do not stabilize by resonance. So you cannot transfer the negative electron to any carbon. It will stick to oxygen only. Like here, alcohol, the electrons will only be at the electronegative atom oxygen only. Same goes for water. It will only stay at the oxygen atom. No resonance effect in water and alkoxide ion. Therefore, aliphatic alcohol is less acidic than phenol. But the most acidic is carboxylate ion because it has two oxygen atoms where it can delocalize. The electron can delocalize between these two oxygen atoms. Inductive effect, the second factor. Inductive effect, the second factor that makes carboxylic acid more acidic is the inductive effect. Inductive effect is the shift in electron density from one atom to another to form a polar bond. So here between O and then H. Okay, O and H different electronegativity, so it is polar bond. When the electron can be shift, due to different electronegativity, we can say it is inductive effect. Right? So in carboxylic acid here, C double bond O, between this carbon and oxygen, oxygen is more electronegative than carbon. So oxygen attracts electron, these 4 electrons closer to itself, making this oxygen delta minus. And this carbon has the 4 electron further than this carbon. So it makes this carbon delta plus. So when this oxygen negatively charged, the oxygen in carbonyl groups acts as powerful electron withdrawing. Electron withdrawing means this oxygen withdraws the electron towards itself. Means it attracts the electron towards itself. When this happens, when this oxygen of the carbonyl, this is not oxygen carbonyl, this is oxygen carbonyl, oxygen that has double bond. C double bond O, oxygen of the carbonyl, when this oxygen attract or withdraw the electron towards itself. Why it does that? Because this oxygen is more electronegative, so it will attract the electrons towards itself. When this oxygen attracts the electron towards itself, the OH bond will become weaker. This OH bond, electron attracted toward this oxygen, so this OH bond becomes weaker. When this OH bond becomes weaker, it will make the carboxylic acid easier to release the H+, because this bond is weak, so it's easy to release this H+. Okay, that's what makes this carboxylic acid more acidic. Inductive effect by substituent. So inductive effect, you can look at electron withdrawing group and electron donating group. Electron withdrawing group is the group that will withdraw electron towards itself or attract electron towards itself. Electron donating group, the group that will donate the electron. Electron withdrawing group, it will reduce the electron density of electrons at carboxylate group. Means we know that this is O negative, this is delta minus, delta plus. So we know that here rich in electron. When you have electron withdrawing group, this group will attract this electron towards itself. That's what we call electron withdrawing group. It will attract the electron within the bond. There's 4 electrons, there's 2 electrons, it will attract towards itself, electron withdrawing group. So when it attracts the electron towards itself, making this OH, okay, carboxylic acid, we have OH, so making the OH bond weaker. When OH bond is weaker, it's easy to release the H+, make it more acidic. Easy to release H+, making the carboxylic acid with electron withdrawing group more acidic. But when the carboxylic acid has electron donating group, means it donate the electron to the carboxyl part, donate electron to COO, it will increase the density of electron at the carboxylate group. More electron means it will donate more electron at COO. Destabilize the carboxylate ion. More electron here making OH bond stronger. When you have more electron here, the OH bond here is stronger. When OH bond is stronger, it's difficult to release the H+. So the carboxylic acid with electron donating group is less acidic. The effect of electron withdrawing group, for example, we have NO2, FCl, BRI. So basically the group 17 atoms, NO2, these are the example of electron withdrawing group. They will attract the electron towards themselves. An electron withdrawing group reduces the electron density on oxygen in OH. OH in carboxylic acid. So the electron density in OH of carboxylic acid will be withdrawn by them, NO2, FCl, Br, making the OH bond weaker, so H+ can be easily released. Electron withdrawing group stabilizes a conjugate base by removing the electron density from the negatively charged carboxylate ion. So conjugate base is COO-. That is conjugate base, COO-, means the electron withdrawing group will attract the electrons towards itself from COO-. Therefore, the compound becomes more acidic with the presence of electron withdrawing group. When the electron is attracted from COO- to the electron withdrawing group, making the OH weaker, H+ easily released, more acidic. Let's look at the example of electron withdrawing group in carboxylic acid. Here we have 2-chloropropanoic acid and propanoic acid. The Cl here is electron withdrawing group. It will attract the electron from the OH and from C double bond O, from these two, towards itself. Electrons will be attracted. So Cl is an electron withdrawing group. It will withdraw electron, making this OH bond weaker. Why OH bond weaker? Because the electron density between OH is reduced. Why it is reduced? Because it is withdraw. The electrons are withdrawn towards the Cl. So electron density between OH is reduced, making the OH bond weaker. When OH bond is weaker, this H+ can be easily released. Compared to this one, it has no electron withdrawing group at all. So in 2-chloropropanoic acid is more acidic than propanoic acid because H+ is easily removed from this compound compared to this one. Next, here we have the example of the equation. Okay, Cl stabilizes the conjugate base by removing electron density from negatively charged carboxylate ion. So here the Cl stabilizes the conjugate base. This is the conjugate base. Cl stabilizes the conjugate base by removing electron density from negatively charged carboxylate ion. Here O negative, it withdraw electron towards itself. Okay, easily remove H+. So here the compound that has no Cl at all, the propanoic acid. In propanoic acid we have CH3CH2. Okay, CH3CH2. The CH3CH2 destabilizes the conjugate base because CH3, the carbon chain, is the electron donating group. Okay, the carbon chain is electron donating group, means it will donate the electron to this C and then O. That will donate the electron to the carboxylate ion. When it donates the electron to the carboxylate ion, making the electron density between OH higher electron density between OH. So the bond between OH is stronger, making difficult to release the H+. So the CH3CH2 destabilizes the conjugate base. It destabilizes the conjugate base by donating the electron onto the negatively charged carboxylate ion. Okay, the presence of electron withdrawing groups makes the acidity increase. So this is the inductive electron withdrawal. The electron will move to the electron withdrawing group, the Cl. There are a few factors in electron withdrawing group. First, we look at the electronegativity. Both F and Cl, both group 17, so both electron withdrawing group. Which one is more acidic? The one with F or the one with Cl? The position are the same at this carbon. The carbon beside C double bond O, the position are the same, but the difference is the atom. Group 17, fluorine and chlorine. If you look at the electronegativity, fluorine is higher than chlorine, means the fluorine has the ability to attract electron more than chlorine. So the electron density on oxygen of OH in 2-fluoropropanoic acid is less. Okay, electron density of here on oxygen, electron density here is less than electron density here because F is more electronegative. Means this F can withdraw the electron towards itself stronger than Cl. Why? Because electronegativity of F is higher than Cl. The ability to attract the electron density towards Cl here is less than F. Therefore, H plus is easily released in F. In 2-fluoropropanoic acid, it's easily to remove H plus compared to this one because F is more electronegative. So we can conclude that the more electronegative the substituent, the acidity of acid increase. Next, number of electron withdrawing group. We are comparing between the compound that has 2 chlorine and the compound that has 1 chlorine, both carboxylic acid. Okay, in the compound that has 2 chlorine, it is able to withdraw the electron more than 1 chlorine only. Okay, it makes the OH bond here weaker than the OH bond here because you have 2 electron withdrawing group. So the electron density on OH is less than the electron density of the O here. Okay, because you have 2 Cl that is in the carboxylic acid. So when you have more electron withdrawing group, the H plus is easily released. The greater the number of electron withdrawing group, the acidity of acid increase. Finally, the position of electron withdrawing group. Both have electron withdrawing group, both have the same electron withdrawing group, but the positions are different. Here at carbon number 2, this compound at carbon number 4. So at carbon number 4, it's much further than carbon number 2 in terms of looking at the position of COOH. Okay, here Cl is further towards COOH compared to Cl. This Cl is nearer to the COOH. The distance between Cl atom and carboxyl group in 2-chlorobutanoic acid is nearer than in 4-chlorobutanoic acid. The OH bond in 2-chlorobutanoic acid is weaker than the 4-chlorobutanoic acid. Okay, so the OH bond here is weaker because the position of Cl is nearer. The ability to withdraw the electron towards the Cl is stronger than the ability for this one because this is further. So OH group in 4-chlorobutanoic acid, this OH bond is stronger than this OH bond. This OH bond is weaker. So that what makes the H plus easily released in 2-chlorobutanoic acid. we can conclude that the more closer the electron withdrawing group to the COOH, the acidity of the acid increase. Now we're looking at electron donating group. We donate the electron to the carboxyl group. R is an electron donating group. The size of R group in propanoic acid is larger in ethanoic acid. So here, ethanoic acid, 1 carbon only, propanoic acid, 2 carbon. So the size of R group in propanoic acid is bigger than ethanoic acid. When it is bigger means the CH3CH2 is stronger electron donating group. The bigger the R can donate more electron, the stronger electron donating group, which makes the electron density at the OH group is higher because it can donate more. So the electron in here between OH is higher. So the OH bond here is stronger. When the OH bond here is stronger, it is difficult to release the H+. When it is difficult to release the H+, making this less acidic. This is more acidic, easier to release H+ because small electron donating group. Bigger electron donating group will donate the electron more. The presence of electron donating group decreases the acidity of acid. We can conclude that the larger the electron donating group, the acidity decreases. The presence of electron donating group decreases the acidity of the acid. The larger the electron donating group, the acidity decreases. So ethanoic acid is more acidic compared to propanoic acid. Here the ability to release H+ in ethanoic acid is higher than in propanoic acid. So it's easier to release H+ when you have small R group